Hello everyone, in this video we'll see binary tree types. Last video we just saw the introduction to binary trees, but in this video there are several versions of binary trees are available, so we'll see one by one. The first binary tree we're going to look at is perfect binary trees. By formally we can state a binary tree is a perfect binary tree in which all internal nodes have two children and all the leaf nodes are at the same level. This perfect binary tree, you can see all these internal nodes are filled and it has two children, and here you can see this last level, the leaf levels all are in the same level. So this can be called as a perfect binary trees. Here you can see all these nodes are filled, so that's the reason it's perfect. So next one is complete binary tree. By formal we can state a binary tree is a complete binary tree if all the levels are completely filled except the last, possibly the last level. In this tree you can see this last level is here some nodes are left yet to fill. So here you can say this is a complete binary tree because only the last level is not filled, but their internal levels are filled. That's the reason it's complete. And the next one is full binary tree. Formally we can state it as a binary tree is a full binary tree if every node has 0 or 2 children. Here in this example you can see this node 2 also don't have any children, and 3, 5, these nodes also having no children. So this is called a full binary tree. You can see this tree, a perfect tree also, you can call it as full binary tree. But in case if I have like this, then it is not, because here you have only one. This can't be called as full binary tree because this node is having one children. Okay, the next is balanced binary trees. We can formally state it as a binary tree is balanced if the height of the tree is O log n, where n is the number of nodes and d is at most 1. What this statement means is I have a node and I have left and right subtrees. This height of this left and right subtrees should be differ by at most 1. So then it is called a balanced binary trees. You could have heard of ABL trees, and there are a lot of binary balanced binary trees are there. So here you can see this node is having don't have any right or left subtree, so that's the reason it's d is 0, and here you don't have a right subtree and here you have left subtree, so the difference of this height is 1. So, but you can go far to the root and you can notice here the left subtree having the height 4 and don't have any right subtree, so the difference will be 4. So this tree can't be called as a balanced binary tree. This is the balanced binary tree. In this also some of the nodes are missing, but if you calculate the difference between these nodes, here the d will be equal to 1, but when you go to this node 2, d will be equal to 0 because it have the height of two left and right subtrees. So this is called as a balanced binary trees, and this is the formula to calculate that distance, height of the left subtree and height of the right subtree and modulo of the value it goes to that node. The next one is skewed binary trees. Here it is skewed called means it has only the left direction and the right direction, either of the direction will come. So formally we can state a skewed binary tree is a pathological or degenerate tree in which the tree is either dominated by the left nodes or the right nodes. You can see in this example here we have only at the left side, and in this example also you can see only the right side. These trees will be helpful for the packagings and libraries buildings. Those kind of applications are there. So we have seen this types of binary trees are there, and next we'll go to the properties of this binary trees. There are some 6 properties are available for this binary trees. First statement is the maximum number of nodes at level L of a binary tree is 2 power L. Here I have a level called 0. Here this level is 0. This is 0, and this is 1, and this is 2, and this is 3. So how do we calculate this is, you have to just write a formula in calculator. 2 power, here you have 3, so 3, 8 nodes, so 8 nodes must be there. So 1 2 3 4 5 6 7 and 8. This is how we can calculate this number of nodes at a level L. So it starts from 0 and 1 2 3, it goes on. The next one is the maximum number of nodes in a binary tree of height 2 power is 2 power h minus 1. The maximum number of nodes. Here I have the 3 levels, so the height is 4. So what I can calculate is 2 power 4 is 16 minus 1. So 15 nodes are there. Here you can see in this tree, here there are 8 nodes and 4 nodes, so 12, 13, 14 and 15 are there. So 15 nodes are, so this rule is applicable. Then in a binary tree with n nodes, the minimum possible height is log 2 n plus 1. So here you have 2 nodes, here you have 3 nodes, then the minimum possible height is it will be like log 2, so log 2 of n plus 1. So here we have 3 nodes, so 3 plus 1 is 4, and if you have this log, if you take the log 2, then the answer will be 2. So the minimum possible height is, here you can see there are 2, 1 and 2. So the next is a binary tree with L leaves has at least log 2 L mod plus 1 levels. Here I have 2 leaves, this leaf and this leaf. So log 2 of 2 is 1 plus 1. So there are 2 levels, 1 and 2. So this rule also is perfect. And then in a binary tree, every node has 0 or 2 children. The number of leaf nodes is always more than 1 nodes with 2 children. Here you can see in this tree, you can say these tree nodes are the nodes which having 2 children, but these nodes don't have any children, so these are all leaf nodes. So if you count these nodes, 2 4 and 6, and the internal nodes are 5, so 6 equal to 5 plus 1. That's what this statement is. The binary tree with where every node has 0 or 2 children, the number of leaf nodes, these nodes always one more than the nodes with having the two children. Here you can see these nodes having 2 children and these leaves are having 0 children, so that's why it's leaf, and these numbers will be always more than plus 1 of this cloud count. Okay, the next is, in a non-empty binary tree, if n is the total number of nodes and e is the total number of edge is n minus 1, so there must be n minus 1. So n is the number of nodes. You can see this 3 nodes are there, and minus 1 means there will be this one edge and this one edge, so e equal to 2. That's what this property is. So hope you understood all these properties, and we'll see the implementations of these binary trees in the next video. Thank you for watching.